You probably understand how you can use an integral to calculate a 2D area or to calculate some things in 3 dimensions such as volume. I want to show you how to calculate something one-dimensional, which is the length of a curve. So let's say this is our curve, y equals f of x, from x equals a to x equals b. We want to calculate the exact length of that curve. So maybe you've got like a machine traveling down some kind of path in 2 dimensions or 3 dimensions, and you need to know how long that path is. You can approximate the length of the path by breaking this interval up into pieces and just using a straight line along each of those pieces. Whoops. All right, so 1 straight line, 2 straight lines, 3 straight lines, 4. It's easy to calculate the length of a straight line. So if you break it up into pieces, calculate the length of each of those lines and add them up, that gives you an approximation. And just like with the other integrals, if you use more pieces, more lines for your approximation, your error will be less, your approximation will be better. And then to get the exact amount, you'll take the limit as the number of pieces goes to infinity, which is the same thing as taking the limit as this width goes to 0. So that's what we'll do. Now, to get our equation, we're going to have first the approximation. So to get the length of this thing, let's say I want the length of this piece. I know that this length is delta x, and I'm going to call this length delta y. So if you let x change a little bit in your function, there's a corresponding change in y. And then I'll just use Pythagorean theorem right now to solve for that hypotenuse. So I get the square root of delta x squared plus delta y squared. That's the thing that gives me the approximation when I add up those pieces. When I take the limit as the change in x goes to 0, it turns into an integral. And I still have this square root of that stuff. But notice, in our Riemann sums, and even in, when you're calculating volume, when you took the process of going from the approximation to the integral, you had some function times a change in x, or times a change in y, and I don't have it written like that yet. So I'm going to do a little algebra to get it in that form. Then the change in x piece will turn into dx over here in symbols. So I'm going to factor out a delta x squared from each of these pieces, and then once I factor that out from each of these pieces, the square root of delta x squared will just be delta x. I'm just going to assume it's positive. So this is the same thing as the sum of the square root of whatever's left over in here after factoring out the delta x squared times delta x. So if I factor out delta x squared from here, I get a 1. If I factor out delta x squared from this term, I end up with delta y squared over delta x squared. And in the process of taking the limit as the change in x goes to 0, change in y over change in x, you may remember from Calculus 1 and the definition of derivatives, this just turns into the derivative of y with respect to x. So that's from the difference quotient. If you use these symbols in Calculus 1, then this is really simple for you to see. But you may not have used those symbols, so you may have to think about it a little bit. But this just turns into 1 plus the derivative of y with respect to x, which I'll write as f prime of x squared. And then the delta x turns into dx. We're going from a to b. So that's the formula that you get. As a quick side note, instead of doing this algebra, you could also use the mean value theorem, if you're familiar with that, to say that this change in y is going to be equal to the slope. It's the slope of this line times the delta x, and the slope of this line is equal to the slope of the tangent line for some special value of x between a and b, or between here and here. So you could immediately go and say this is equal to f prime of x times delta x, or f prime of x star, where this is your x star. If you don't remember the mean value theorem, don't worry about it. You can just do the algebra. The other thing that I wanted to show you is how to calculate the surface area of a curved object when you've just taken a line and rotated it around an axis. So it's going to be really similar to this, but to get our approximation, we're going to have pieces that look something like this. So instead of a curved line, I'm going to use a straight line like I did over here. And then what I'll get is a ribbon type of thing. So it's like the outside of a disc, it's a ribbon, but it's not flat here or flat here. I'm using a slanted line here and a slanted line here to make sure I capture the way the function changes all the way around this object. So to get my approximation of the surface area, I add up the surface area of all these ribbons. And when you do that, to think about what that calculation is, I'm going to split apart this ribbon and unfold it. And then it looks something like this. These edges are slanted. If I go all the way around, that's just the diameter 2 pi r, where r, the radius, is just the y value, or the function value on this curve. And then these slanted pieces are not just delta x. They're actually this kind of thing. So I need to use this guy. So in the approximation, it would be exactly this length would be that square root delta x squared plus delta y squared. And then when you take the limit, again, you'll do the factoring out, take the limit, and you'll get the square root of 1 plus f prime of x squared. So to get the actual formula for that one, remember I'm adding up the surface areas of all those ribbons. So I'm going to take, this is after I've split it apart, I'm going to take 2 pi f of x times this height. If I do 2 pi f of x times the length of this, that gives me a good approximation of this area. And then when I take the limit, I get the exact surface area. So when you take that limit, you're going to get the integral of 2 pi f of x times this piece here. So I'm going to write it down here, times the square root of 1 plus f prime squared dx, and you're going from a to b. This is called arc length, and this is surface area for an object of revolution.